Hello, my name's Peyton Thibodeau, and I'll be covering the integrating factor method. Let's see if I can keep this video concise this time. So I will be covering the general form of a first-order differential equation. So first order just means it only goes up to the first derivative, and we're only talking about ordinary differential equations. So that means no partial differential, no partial derivatives. And the integrating factor method, which is the main focus of this, and that is a way we can use to solve differential equations. So first up, here we have the general form of a first-order differential equation. We have first derivative plus a of x times y equals f of x. A of x and f of x can be any function as long as it is continuous. It does have to be continuous. And this is the form that you'll want to get your equation into for solving using the integrating factor method. So integrating factor method, what is it? Why is it useful? So an integrating factor is a function that is chosen to facilitate, or when it pertains to math, used to facilitate for solving an equation, differential equations. So we'll find an integrating factor, which I'll refer to as mu. Once we have found it, we can then multiply it throughout our differential equation, and we can use that to get it into a form that's much easier to work with and to integrate. So how and why it works. Right here, you can see again the general form of a differential equation. And using product and chain rule, after we found our mu, or integrating factor, we can get it into the second form right here, where it's the derivative of mu times y, again, mu is our integrating factor, equals mu times the right side. And this right here is something much easier to integrate and work with than just using the general form. So to get our integrating factor, again, right here, we have the general form, p of x, q of x, any function as long as it's continuous. And the integrating factor is equal to e to the power of the integral of p of x is our middle function here, dx. And that is how you will get your integrating factor. You then go through, multiply that across your differential equation, and you can get into a form that's easier to work with. So now I'm going to go over an example I've worked out. So let's see. Right here we have ty prime plus y equals sine of t, and we are given an initial condition here. So first thing, we have to get it to the general form, so we divide everything by t, and that gives us y prime plus, and you see right here in the center, I've separated 1 over t times y. 1 over our t is our middle function, and we need that to find our integrating factor. And again, we divide the right side by t also, because you have to do equal to both sides. So right here, we see p of x, 1 over t. And again, mu is equal to e to the integral of our function dt. In this case, 1 over t. And right here, you see 1 over t, as you know, is integrated. You just get the natural log of t. We don't have to worry about plus c in this scenario, because any constant would work. So to make it easier on ourselves, we just assume it's 0. And that gives us the easiest the easiest mu to work with. So then we go back to here, e to our result, and e and the natural log cancel out, so mu just ends up being t. We then go back in, we multiply everything in our equation by t, so t times y prime. Right here, there's nothing here because there was 1 divided by t. That times t cancels out, so this is like a 1. And sine of t here, it was divided by t. Then when we multiply it by mu, that also cancels out. So there's the t here and here, canceled out. Now that we have our left side here, we can put it into this form here. So we have the derivative of t times y dt. Derivative, and equals to sine of t dt. Then what we want to do is integrate both sides. So on this left side, the integral and the derivative cancels out, so we're just left with t times y. And on the right side, the integral of sine of t dt gives us negative cosine of t. So right here we have t times y equals, equals negative cosine of t plus c. And we want to get this in the form of y equals, so we divide everything by t. And that gives us our general solution right here. General solution, and we get our initial condition from earlier, and using that, we can solve this for a specific case. So given this initial condition, when y is equal to 1, negative cosine of pi divided by 2 plus c, and then divide by t, which in this case is pi divided by 2. We know cosine of pi divided by 2 is just 0, so that just goes to 0 here. And we have 0 plus c divided by pi divided by 2. So we need this to equal to 1, so c has to be equal to pi divided by 2. And that's where we get this. Then we plug that back into our general form, and this is our specific solution. Thank you for watching.